Going to go to Einstein's equations in this last lecture. General relativity is a vast subject, and thank you for your patience. Uh, as you know, it takes a full semester or so to go through the requisite material to understand the subject. I've tried to condense it into 3 lectures because the refresher course only has so many lectures. But so I can totally understand if the 3 lectures are not leaving you enough time to dig deeper and understand each slide. But this is where I hope that you will be able to find time later in this lockdown where you can actually pick up a book and follow up on the material shown in these slides. And if you do it soon, perhaps you'll actually be able to understand more easily. But I also realize some of you have already studied it, and this is refreshing your knowledge of it. All right, so moving on. Towards the end of the last lecture, we introduced vector derivatives. In the process, we understood that the covariant derivative of the components of a vector are not always the same as their ordinary derivatives, but also may get contributions from either the fact that the coordinate system is curvilinear or the fact that the space-time you're dealing with is curved. So those bring about these Christoffel symbols. And then I also mentioned that, you can have prescriptions where the metric is already given to you. And then by taking the derivatives of the metric, you can find the Christoffel symbol using this expression. Remember that alpha, mu, nu are free indices on both sides. So beta here is a contracted index, okay? So this is actually not very difficult to remember. The last term with the negative sign actually has both these free indices, mu, nu, on the metric itself, g, mu, nu, right? And beta, the derivative index, is the contracted index. In the other 2 terms with positive signs, only one of the 2 free indices is retained on the metric. In the first case, it is mu. In the second case, it is nu. And the other index on the metric is the contracted index beta. Now, here I will observe a point, and that is that you may have heard that one thing Einstein heavily depended on for coming up with his equations of general relativity was the principle of equivalence, right? So in one description of it, one would say that you can get into a freely falling frame, and so locally, therefore, in time and space, you can find yourself in a situation where you don't feel the effects of gravity, right? In other words, locally, you are as if you're in a flat space-time, which means if that is true, then the Christoffel symbols should be 0 in that frame. And the answer is yes. So locally, if you find yourself in such a frame, like an elevator, then momentarily in the coordinate systems of the elevator, the metric will be Minkowskian, right? And so remember, that is why I say, more precisely, the components of the metric locally will be Minkowskian. So these derivatives will be 0, and in the Cartesian coordinates, and the Christoffel symbols will be 0. And so you may say that, yeah, the effect of gravity will go away. Because ultimately, the effect of curvature or gravity, as you're realizing through these derivatives, comes in from these Christoffel symbols, right? So that is true. You can make such a coordinate transformation, but remember that it is only local. Local meaning at a point in space and time. You just have to wait a little longer to see that actually the space-time itself is not Minkowskian. Little longer means that, for example, if you drop 2 balls, right? Locally, the balls are falling with you, and it is as if everybody is in flat space-time. But if you wait a little longer in that elevator, freely falling elevator, you'll find that the balls actually come closer to each other, right? And in other words, they are actually falling in the tidal field of the Earth. That is, the gravity of Earth is actually changing as you descend in space, okay, through different heights. A better way to describe this would be that if you had 4 balls, okay, 2 horizontally separated and 2 others vertically separated. In that situation, the stridal, compression and stretching is even more stark, right? So as you fall, the two horizontally separated balls will come closer, and the two vertically separated balls will actually get further apart. And don't try this outside a black hole, a stellar-mass black hole, because then automatically that means that you'll be stretched by the tidal forces of the black hole, because the gravity at your feet is very different, much stronger than the gravity at your head. So you'll be torn apart. Again, write your questions for Shalab, and I'm going to take questions in about 15-20 minutes, and then at the end of the lecture. Okay, and then I also, because one of you asked an interesting question, I said that, yeah, covariant derivatives are going to be important because they're going to tell us how vectors can, at different points in space, such as on the curve, can be related to each other. If they are actually the same vector, only parallel, as best you can define parallel on a curved manifold, right? But then why you limit yourself to just vectors, right? You can ask the same questions for the dual vectors or some general tensor. That two tensors defined at 2 points separated by some distance along the curve, are they actually the same tensor, parallelly transported? So to answer those questions, we will need the help of the covariant derivative, and then define the covariant derivative towards the end of the last lecture. But the key definition is this, which you should remember, that the covariant derivative of the components of a vector are related to the ordinary derivatives plus this contraction of the Christoffel symbols with the with the components of the vector. So to understand curvature, I've already hinted that we need to understand parallel transport, but that is how we can judge whether these green vectors are parallel to each other on a curved manifold. On a flat manifold, it's trivial, but on a curved manifold, how do we do that? And one way to do it is to say, okay, if take any two vectors, any two green vectors, connect them with a curve, and by definition, curve is a path or a set of points that are parameterized. So there is some parameter here, for example, the lambda parameter. If this is a time-like curve, then the time measured by a clock, okay, that proper time tau could be the parameter. So then this lambda will be tau. But the point is, we want to understand how the components of this vector vary as we go around this curve or go along this curve. Okay, and that is how we are ultimately going to judge whether the vector is parallel transported or not. But I'll return to this in a minute. But why are we interested in it? I mentioned curvature. This is why we're interested in it. One way to understand curvature is the following. You have a sphere here, right? This is not space-time. This is just a two-dimensional surface that is curved, right? The two-dimensional surface is that of sphere. It is two-dimensional. It needs two coordinates to specify all the points on it, like the theta coordinate, the polar angle, and the phi coordinate, the azimuthal coordinate, right? So theta and phi, those two coordinates are needed, or latitude or longitude also. Now, how do you judge whether this is curved or not? There are actually a set of different ways to do it. One, graphically useful way is that, okay, you make a triangle here, okay? And I'm going to use some loose language deliberately in the beginning. I'm going to make it more compact in a moment. But draw a triangle here, and you know that if this was flat, then the sum of the internal angles in that triangle will be 180 degrees. Now, if it is positively curved, the statement is that then the sum of the internal angles of the triangle will be greater than 180 degrees. If it is negatively curved, and again, colloquially speaking, like the surface of a saddle at certain points, then the sum of the internal angles of the triangle drawn on it will be less than 180 degrees. Okay. Now, these are loose statements, and I'll tell you why. Number one, the negative curvature or hyperbolic slices are difficult to describe because there is actually a theorem that tells us that, and that's why I've not done it here, that you cannot embed a two-dimensional hyperbolic surface in 3 dimensions. Okay? And that is why we cannot draw a diagram, even using perspective, of negatively curved 2-dimensional spaces, right? And that is why the saddle is only an approximate description of this, like the saddle that you place on the top of a horse before you sit on it. right? That's only an approximate description of a negatively curved space. In fact, it is negatively curved in one dimension, but positive in the other dimension. But you get the idea that if you try to draw a triangle there, the internal angles will somehow to be less than 180 degrees. The other loose language was that if you think about it, what I just said about drawing a triangle here will result in internal angles greater than 180 degrees. That also is not correct, meaning it's not always true. You can actually draw triangles on a sphere. This is coming close to it, okay? This triangle is coming close to it, where the sum of the internal angles is not greater than 180 degrees. Okay, so therefore one has to be very careful in qualifying these statements. The correct statement is that when you draw a triangle, do it exactly like you do for Euclidean spaces. Now that's not a very helpful statement. What is meant there is that you draw the straightest possible lines in Euclidean space, but and then make a triangle with them. But the straightest possible lines on a sphere, it will turn out are what are called geodesics. Okay, these also happen to be lines that connect any two points with a curve with the shortest or the longest length. So it's very important that when you make a triangle, the sides of the triangle are actually geodesics. That is, they are of extremal length. So if you choose one of your vertices of the triangle to be the pole, just for ease of drawing, then indeed any one of the longitudes would be a geodesic, because all great circles are geodesics, meaning take any 2 points on a longitude, such as the North Pole here and a pole on the equator there, then the shortest possible line connecting these 2 points is actually a longitude. Any other curve will have a longer length. Okay, but the path joining these 2 points can also be the longest, and that would be the complement of the same longitude going around the Earth and coming back. Okay, so it is indeed the case that both of these are parts of a geodesic, and that geodesic is this specific longitude. Your other leg or side of the triangle could be another longitude, such as this one. So two longitudes, both geodesics, you take the triangle sides, 2 sides from those, but the third one has to be a geodesic as well. And you should be able to show this on your own later, that if you take an arbitrary latitude, and then an arbitrary latitude is not the shortest or the longest curve joining any 2 points. Okay, and indeed that is why if you fly, going from one point to another city on the same latitude, if the flight is permitted to take a geodesic path, it's not going to fly along the latitude. To save fuel, of course, air currents also matter, but for the moment you ignore them, it will actually travel a different path. Okay, it will try to go on a geodesic to save fuel. So none of these latitudes are actually geodesics. In fact, the only latitude that is a geodesic is the equator. So that is why I choose my triangle like this. Okay, all the legs are now parts of geodesics. And now, indeed, it is true that when you sum up the internal angles, they turn out to be greater than 180 degrees. So that tells you that this is a positively curved 2-dimensional surface. But another way of measuring curvature is to do the following. If you take a vector, let us see how to do it. Let us take this vector here. Okay, let us take it up to the pole, the red vector. So, but I have to take it in such a way that it remains unchanging with respect to the tangent vector at any point, okay, of that curve. And then when I'm at the pole, let me come down the other side of this triangle. Okay, once again, I bring down the red vector in such a way that its orientation with respect to the tangent vector along this longitude remains the same, just as its magnitude does. Okay? So that brings me to this red vector at the equator. And then let me translate it back using the same prescription to the original point. And you notice that the orientation of this vector has actually drastically changed. So the amount of change here will tell you some information about the integrated curvature in this triangle. But you can do the same thing on a very small location, okay, just around this point. Take it around a triangle, but or for that matter, along a rhombus or just a loop, okay? And this is one way of judging. If the vector does not return to its initial orientation, then it means that, in fact, the degree of change in the vector will tell you how curved the manifold is locally at and around that point. So to be able to define curvature, therefore, I need to first know how to parallelly translate my vector. So that is what brings us to the initial point. Remember, along this curve, the coordinates x, y, z, and t of any point can be written as functions of the parameter lambda, where lambda is the one-dimensional parameter on the curve. And also the tangent vector on the curve then will be just this, how the coordinates of any of these points change with lambda. So dx beta by d lambda is indeed nothing but a 4 vector. Okay? And it will translate like the components of a 4 vector, or just a vector. So how do I judge whether some other vector, the green vector denoted by v, so u is the tangent vector, red, on this curve, and v is some arbitrary vector, green vector, which I want to parallelly transport along the blue curve. So how do I do that? The statement is that the vector v should not change along this curve. That means its change with respect to lambda should be 0. Okay, anywhere, if it's to be parallel transport anywhere on the curve. Now this statement, d by d lambda v equal to 0, is the same as what I've written here on the right. And this is the chain rule, right? Because d by d lambda can be written as dx beta by d lambda times d by dx beta acting on v. But dx beta by d lambda is just u beta. That is what is defining here, right? And then d by d beta, this is not the ordinary derivative, this is the covariant derivative. So d by d beta, so it's not del by del beta, it's d by d beta. That is the covariant derivative of v. Okay? Actually, it doesn't matter. The fact is that any derivative of the vector v most generally is the covariant derivative. And that is the same thing as I had shown. Yeah, basically here, that any derivative of the covariant derivative, any derivative of v will have an ordinary derivative piece of its components, and then another piece together, which will make the derivative to be covariant derivative. So that's what we're doing here. Okay, so we are taking the, so this is just dx beta by d lambda, and then that is multiplied with dx beta contracted over beta acting on v, but that's the same thing as u beta contracted with the covariant derivative of v alpha with x beta. Okay. So this has to be 0 is what the statement is, or the requirement is for parallel transporting v. This both means that not only the parallelly transported vector has the same magnitude, but also the same angle with respect to the tangent vector at any point on that curve. And so this is the same thing as, this is another notation, okay? I'm just introducing them because different books use them, so they should not perplex you. So this is the same statement as saying that the covariant derivative of v with respect to u because lambda parameterizes the curve to which u is the tangent vector. So covariant derivative of v with respect to u is 0. These are all the same statements, but in component form, this is the statement, and this is the easiest to deal with to make calculations, right? Now, what is a geodesic? A geodesic, I told you one definition of a geodesic. A geodesic is a curve that is of extremal length between any 2 points. It turns out, so what will you do? To find the equation of such a curve, you will take an infinitesimal element here, find its length, and then you integrate it between these 2 points. But if it is extremal, then you will vary that integral, right? With respect to other possible paths between those 2 points. And that integral variation, right? The variation of that integral will actually give you an equation of motion, very much like the Euler-Lagrange equations in classical mechanics. It turns out that the Euler-Lagrange equation for geodesics is precisely this equation, but with a v, which is nothing but the tangent vector itself to that curve. Okay, so another way of saying that is that a geodesic is a curve that parallel transports its own tangent vector. So it is this same equation with v being u itself, because u is the tangent vector to that curve with parameter lambda. So this is the statement. They are equivalent statement. Okay, parallel transport means that the geodesic, or rather a geodesic is a curve that parallel transports its own tangent vector, which is this equation, but that's the same expression as what you will get by extremizing the path connecting any 2 points. So that path of extremal length is also geodesic. It's the same equation. And this indeed looks like a Euler-Lagrange equation, if you recall. Okay. So how do we get this? We get this by noting that this is nothing but the same equation as on the top, with V replaced by U, because we are parallel transporting the tangent vector itself. And this is equal to 0. So that is equal to 0. But then the covariant derivative of U alpha with X beta is the ordinary derivative and the Christoffel symbol term, right? So this is what you get. By the way, I should clarify that if you looked at the definition of the Christoffel symbols in terms of the metric derivative, you would have realized that the Christoffel symbol is symmetric under the interchange of mu and beta. Okay, and so nothing is lost here because we are contracting with an object which is also symmetric under the interchange of mu and beta. But now I can replace u mu with this definition, dx mu by d lambda. So when I replace it, this is what I get for this last two u's. But then the ordinary derivative, there's only one comma here, the ordinary derivative of u alpha can be re-expressed like this. Okay. Here again, I'm using that chain rule to make some simplifications. Okay. Basically, what is happening is that this u beta has a dx beta by d lambda, but then this ordinary derivative also has a dx beta in the denominator. So in some sense, I'm getting rid of them. So this is what I get. So from the first one, I get d by d lambda, and u alpha itself, by definition, has a dx alpha by d lambda. So this is a second order differential equation, and this is the equation of a geodesic. Okay. So remember this: the way to calculate geodesics on any space or space-time where the metric is given is that you compute the Christoffel symbols, right? And then you solve this equation for all possible values of alpha. The beauty is that alpha is the only free index. So there are only 4 equations here. Okay, the rest are contractions. So you have 4 equations, and you have to solve those 4 equations, understandably, because those 4 equations are for the 4 coordinates of points on any curve. So by solving for those coordinates, you get curves, which are the geodesics. If you solve it for the 2-dimensional metric on the sphere, you will find that this equation is nothing but the equation of all the great circles. So an infinity of longitudes and an infinity, basically an infinity of longitudes, but with a rotational symmetry where the poles can be rotated. Okay. Now, why was this important? Because I gave you prelude by saying that we will need this to define curvature, right? Curvature, another way of saying it is that, okay, you basically have to ask, how is this vector changing as you take it along that path? But then you have to change that changed vector further. So in that sense, there are 2 derivatives involved of V alpha. Okay. Now, this is very similar to the tidal experiment I was asking you to perform in a freely falling elevator. That there, you can get into a coordinate system where the Christoffel symbols can be made to vanish. Another way of saying that is that the metric can be made flat. So the first derivative of the metric is not sufficient to tell me whether there is curvature. I need 2 derivatives of the metric. Okay, and that makes sense. That is because tidal stretches or tidal acceleration also involves 2 derivatives of coordinate separations, right? So that is what is happening here. So you take a vector. Remember, the vector will have a coordinate separation like dx beta, but then you have to take 2 of its derivatives, okay, to take it around a path. But one way of asking this question is that, okay, so actually replace this triangle maybe with a with a parallelogram. So you take the vector up along this line and then along this line, but making sure that this is a geodesic. And then you take the same vector first along the equator, but then along a longitude. And then, so these 2 operations are like these 2 operations shown in derivatives, but with alpha interchange with beta. It's like, alpha could be the theta coordinate and beta could be the phi coordinate, right? Then the second operation, you change things along the phi coordinate and then change things along the theta coordinate, right? And then see whether your changed vectors are the same or are they different. Okay, if they are the same, then there is no curvature. If they are different, then that's the measure of the curvature. How different they are can be measured in terms of the vector itself. That makes sense, because if the vector itself is scaled up, then the change can also be scaled up by that same factor. So I want that scaling to eventually go away, leaving me, but this relation makes sense. So the longer the vector, the change in the vector will also be that much more. Okay? So this anti-commutating derivatives on V mu should be proportional to V mu itself, but the proportionality factor can be determined. So this is like a linear expansion. Okay, I will be using this expansion again and again. So this is really V mu, the change in V mu, when we take it along two different paths to the final endpoint, and we measure this change as a linear expansion in V mu itself, and these expansion coefficients are these R mu, nu, alpha, betas. There are these many free indices because alpha, beta, mu are free indices on the left-hand side. So, but remember that alpha, beta is antisymmetric under the interchange of alpha with beta on the left-hand side. So therefore, this linear, this expansion coefficient, which is by the way called the Riemann tensor coefficients, here also alpha beta interchange makes it antisymmetric. Okay. So one thing you can show is that if you take the covariant derivative of the covariant derivative of this and then take the difference, clearly you will have derivatives of the Christoffel symbol, right? Because a single covariant derivative of a vector gives you one Christoffel symbol. Another covariant derivative will take the derivative of that Christoffel symbol. But you will also have mixtures or quadratics of Christoffel symbols from the two covariant derivatives. So you can show that when you expand these covariant derivatives, the Riemann tensor components actually have four terms. The first two terms have ordinary derivatives of the Christoffel symbol. That is what this comma nu means. And then you also have quadratics in the Christoffel symbols, like here. Okay, and once again, you can show that indeed, because they have written mu nu as the last two indices, the right-hand side will be antisymmetric under the interchange of mu n. So these first two terms will develop a minus sign, right, when you change mu with mu. And here too, when you change nu and mu, you develop a minus sign. There's a little minus sign here. You can do interesting. So by the way, so this is actually a measure of curvature. If this is 0, that means locally there is no curvature. If this is non-zero, that means locally there is curvature. Okay? This is not a scalar. So therefore, this is not a scalar definition of curvature. Its value will change from one frame to the other. Okay? But it is true that if all of these components are 0 in one frame, then in any other frame, all of them will remain 0. I mean, that is what coordinate transformation of components of a tensor do, right? So keep that in mind. But it is possible that these are 0. Some of these are 0 in one frame, but not in all frames. So, but a scalar quantity can be created by contracting all of these indices. I'm going to come to that in future. But a motivation for that is to learn how to contract indices on multi-ranked tensors, right? So we are showing an example here. So here I show an example where I contract yeah, so okay, here I'm not contracting. Sorry, I just lower an index. This is an example of lowering an index. Remember, like I lowered the index of B mu from mu up to mu down in the last lecture. So here, similarly, I'm going to lower the sigma index on this Riemann tensor. Remember, this is the same tensor as this one, okay, except that the indices are labeled differently. So here I'm contracting in sigma, and alpha is a free index, but this contraction using metric makes it a different kind of tensor component where all the indices are down. To be specific, this is a 1, 3 tensor, whereas this is a 0, 4 tensor, meaning this tensor acts on 4 vectors to take it to a scalar. Okay. If you write it this way, there is another symmetry property you can prove from this expansion in the Christoffel symbols, and that is that this 0, 4 tensor components, R, alpha, beta, mu, nu, are not only antisymmetric under the interchange of mu and nu, but they also happen to be antisymmetric under the interchange of the first two indices, alpha and beta. So alpha, beta makes it antisymmetric, mu, nu also makes it antisymmetric. There is a further symmetry, which is that uh, swapping the pair alpha beta with mu nu, so that will make it, R mu nu alpha beta. Swapping that pair makes it symmetric. Okay, so it is symmetric under the interchange alpha beta going to mu. These symmetry properties are important because they tell you that this is not, this does not have 4 times 4 times 4 times 4 independent components. Remember, if there were those many independent components, you will have, 4 times 4 is 16, times 4 is 64, times 4 is 256. If all of these were independent components, then there will be 256 elements to keep track of. Thankfully, that's not the case. The number of independent components, because of these symmetries and one additional symmetry I'm going to come to, make it only have 20 independent components, which means there are 20 curvature components that you have to keep track of, which is not small, but thankfully it is not 256. Okay, so what is that last symmetry I said? So I'll come to that as follows. So this is, I'm just repeating this expression from the previous slide. This is the general expression for the Riemann curvature tensor components in terms of the Christoffel symbol derivatives and their products. Now, as I said, if you go into a local frame, right, you can make that choice where it's locally inertial or Minkowskian. In that case, all of these, the last two terms can be made to vanish because they're just products of Christoffel symbols. Okay, so the Christoffel symbols vanish, they vanish. But the derivatives of the Christoffel symbols don't vanish if the spacetime indeed is curved. And that is what I mean by saying that, yeah, you can go into an elevator where locally things look like Minkowskian, but if you just move slightly, you will see, the separations between these freely falling balls change. Okay, that tidal change is captured in the fact that the derivatives of the Christoffel symbols should not vanish if spacetime there has inherent non-zero curvature. Okay, and so that is why in a locally inertial frame, these terms will go away, but these terms can be expressed in terms of the metric there, or the derivatives of the metric. And so in that local frame, you can express this in terms of double derivatives of the metric. Okay? So these double derivatives actually measure the tidal acceleration. Remember, when I say comma sigma nu, that means that g beta mu here has a derivative with respect to x sigma and a second derivative with respect to x nu. And these are ordinary derivatives, so they interchange. Okay, so that is, so these are the derivatives I get from these two, only these two Christoffel symbol single derivatives. Okay. Now, using this equation, it is easy to show that the Riemann tensor components or their relatives, where you bring down the alpha down using a metric operation like the one shown at the bottom here, bottom left. When you do that, you can show that the Riemann tensor components obey this equation, this identity, where the covariant derivative here of r alpha beta mu nu with respect to lambda plus you keep cyclically moving around this mu nu, the last three indices. So lambda goes in place of mu gets shifted to the right, nu gets shifted to one more right, and this is what you get. And then you again cyclically rotate. Nu goes in the place of lambda, mu goes in the place of mu, lambda goes in the place of mu. So when you do this, this combination is also zero, and this is called the Bianchi identity. Okay, I'll tell you why this is important in a moment. This is actually one other constraint that is required to show that the number of independent elements in the Riemann tensor components are only 20. Okay, if you apply on the previous slide the anti-symmetry under interchange of mu nu and alpha beta respectively, and symmetry under the interchange of this pair, you can show that you actually get 21 independent components. Okay, but if you apply this last one, yeah, that shows you that there are only 20 independent components. So this actually means that in general you will have 20 equations to solve. But if there are symmetries in your spacetime, like if it is a spherically symmetric spacetime, and also if it is static, which is, as I said, mostly true, for example, for the sun, then the time derivatives will vanish also. And so these symmetries can reduce those 20 equations into of the order of a handful of equations. And those are easier to solve to see what the metric structure is like for a static spherically symmetric spacetime. So I'm going to do that towards the end of this lecture. Okay, So a few other identities before I go there. I already showed you one contraction in the past. Here is another contraction. So I start with the 0, 4 tensor components. So alpha, mu, beta, nu are all lower indices. I can contract. Remember, I should not contract alpha and mu. Why? Similarly, I should not contract beta and mu. Remember, the metric tensor is the symmetric tensor. Oh, by the way, this is the inverse of the metric tensor, which has indices upstairs. Okay, but this is another thing you should become conversant with. But basically, G alpha beta contracted with another G alpha beta with alpha beta, or let's say alpha mu with alpha mu downstairs, will give you the Kronecker delta. Okay, so delta alpha mu. So which means that this is the inverse of the 0 to tensor components I showed earlier with G, mu nu down, like the G mu nu here. Okay, so you can contract G mu nu with G alpha beta, let's say with mu replaced with beta here. Then you get G alpha beta contracting G beta nu, and the answer there is delta alpha up, nu down, which is a Kronecker symbol. It has only unity everywhere in the diagonal and zeros in the off diagonals. So that tells you that this is the inverse of this metric. So strictly speaking, these are the components of a 2-0 tensor. But anyway, you can use this to contract alpha and beta, not alpha and mu, because if you contract alpha and mu, you will get 0. Why? That is because this tensor is anti-symmetric under the interchange of alpha mu, whereas this is symmetric under the interchange of those indices. Okay. So you cannot. So in other words, the contraction of alpha mu will give you 0. The contraction of beta nu will give you 0, which is why here I choose to contract alpha with beta. Okay, one from the first pair, another index from the second pair, and that gives me in general something that is non-zero. Okay, so mu is the second component index, and nu is the last index. So this is a 0-2 tensor component, and it is called the Ricci tensor. Okay. By the way, this is teaching you how you can generate different types of tensors just from contraction. This is a symmetric tensor in mu nu. That is because I told you the pair alpha mu can be swapped with the pair beta nu, and that swap is symmetric. So this Ricci tensor components are symmetric under the interchange of mu, which, by the way, is the same thing as saying that the Ricci tensor itself is symmetric, meaning its operation on two vectors A and B is symmetric under the interchange of A and B. I mean, that is what we mean when we say G mu nu is symmetric. That is, the operation of G on two vectors A and B is symmetric. That is, the answer is the same whether you make it operate on A comma B or B comma A. So in that sense, R mu nu is also a symmetric tensor. Okay, if you contract it first, so this can be contracted because mu and nu are not antisymmetric. So when you contract R mu nu with G mu nu, or the inverse of it really, inverse of this guy, then you get a scalar, because now all the indices are gone. They're all contracted. So this scalar is an invariant under any coordinate transformation. Okay, and that is useful to know. Why? That is because, remember, a moment ago I was saying that to be sure that there is no curvature at any given point, you have to appeal to scalar quantities, which are invariant under coordinate transformation, right? So R is one such quantity. Ricci scalar is invariant under coordinate transformation, but you should not deduce your inference on whether the curvature is vanishing or not based on only one curvature scalar. Okay, there are other curvature scalars that are important. Can you think of some? Remember, instead of G mu nu, you can actually contract R mu nu with the inverse of R mu nu. Okay, so instead of this G, think of this as R and mu nu upstairs. You will not get a Ricci scalar, you will get a different scalar, but that is another scalar. So R mu nu contracted with R mu nu down is another curvature scalar. Similarly, you can think of a third scalar where this R alpha mu beta nu are contracted with R alpha beta nu, where alpha beta nu are all upstairs indices. Okay, forget about this G alpha beta. So that new scalar where I'm taking Riemann tensor components and contracting them, that's called the Kreshman scalar. Okay, that is another important scalar that we use to deduce whether the space-time has non-zero curvature at any point of interest or not. All right, so now coming back to the Bianchi identity. So this is the Bianchi identity. if you, sorry, let me create one more tensor. This is the more interesting tensor which I had introduced yesterday, right? So imagine taking the Ricci tensor R mu nu and then subtracting from it half metric tensor G mu nu components multiplied with the scalar R. Okay, this kind of a combination is also a tensor because it is just the sum of two 0-2 tensors. Remember, R is a scalar. So this is the same thing as R by 2, a scalar, times a 0-2 tensor component, right? So the sum of two tensors, or the difference of two tensors of the same type, will also give you a new tensor of the same kind. So this is also a 0-2 tensor. Okay, this is the big G mu nu. This is called the Einstein tensor. Now, why would I do something like this? The reason is going to be somewhat more apparent in a couple of slides. First thing is that this identity that we mentioned, the Bianchi identity, where we showed that because of this property of the Riemann tensor, one can show that it obeys this identity of its covariant derivatives, right? Remember, every term here has a fifth index, which is actually a covariant derivative index, right? This identity, you take it as an assignment. You can show that this identity actually implies that the Einstein tensor obeys this very interesting property. This is the same thing as saying that the covariant derivative of the Einstein tensor is 0. Okay? The covariant derivative of the Einstein tensor is 0. Remember this. You can obtain it by taking the covariant derivative of G mu nu here, and that means you take the covariant derivative of this and this. This will give you two terms. There will be a derivative of R, right? That will just become the ordinary derivative, and there will be a covariant derivative of G mu nu, which is 0 because our covariant derivative is metric compatible, as I told you in the last lecture, right? But you will have a derivative of R, the ordinary derivative. Now, these derivatives can be further expanded using these definitions. So ultimately, these covariant derivatives can be written in terms of the covariant derivatives of the Riemann tensor. And then using this Bianchi identity, you can prove that the covariant derivative of G mu nu contracted in this way is actually 0. This is very important because when Einstein started thinking about, okay, I have so many choices to define curvature. To define curvature, I can use the Riemann tensor or the Ricci tensor or the Ricci scalar or even this tensor. But the beauty about this tensor is that it obeys this identity. These guys, I mean, R mu nu, for example, does not obey this identity. Okay, so because that will be too restrictive. Just like R, if you require that the covariant derivative of R is 0, that means that the derivative of R, the ordinary derivative is 0, which means R cannot be allowed to change from one point in space to the other. That means the curvature of space-time cannot be allowed to change, from one point to the other. That will restrict the type of space-times you have. And that is counterintuitive because I can say, no. I can bring a lump of matter, localize it here, and nothing there. Okay? Then my space-time should respond so that the curvature here is different than the curvature there. But if I equate, like the scalar of G, so G contracted, to be proportional to R, I get an equation of motion, right? That tells me that, okay, my stress tensor can be related to one of these curvature tensors. But then if I don't allow R to change, then that does not allow me to change the stress tensor describing matter or radiation. So I don't want it to be restricted. If I use G mu nu to define my tensor, then it is not restrictive on the T mu nu at all. That is because if you say that, okay, my G mu nu has to be proportional to the stress energy momentum tensor T mu nu, then the fact is that T mu nu also obeys that its covariant derivative is 0, because that is nothing but the conservation statement, that energy momentum stresses, they have to be conserved. So let us give a brief digression to T mu nu. Because of lack of time, I'm not able to give you more details. But this is an example of the T mu nu of a perfect fluid in a special coordinate system where everything is diagonal. Okay, so there is no viscosity and no shear, because if there was shear, then you will have the x momentum changing in the y direction, right? That is shear. So there is force between two surfaces. And those will be off diagonal terms like xy terms and yx terms. So they're not present. Similarly, there is no heat transfer occurring across surfaces. So there is no energy flux. across the x surface or y surface of the z surface, which is why these terms are zero. So this rho being zero this is the energy rho, okay, and then the other index is xyz. This is just the energy flux through x surface, y surface, z surface, and so on and so forth. So these are all zero. Only the diagonals are non-zero. That is because in general a perfect fluid will have some energy density, which is the T00 component, and will have some pressure, right? And pressure has to be isotropic. So that is what this is in this quantum system. There are special examples of T alpha beta even among perfect fluids, namely, dust and the galaxies, given the astronomical distances between them, can be thought of as dust, specks of dust that just, evolve. They can move across space-time or they can expand with the space-time, but they're not mostly colliding with each other. Of course, there are exceptions. But it's a good idealization that we can imagine the matter distributed in the universe as specks of dust. So they're not exerting any pressure on each other because pressure would then require them to have contacts and contact forces. But they have some non-zero density. So pressure is zero. T11, T22, T3 are zero. That is what this statement is. So this is an equation of state. Right? This is a relation between pressure and density, where pressure is zero regardless of density. Another T alpha beta example is radiation, perfect fluid. Here, pressure is 1/3 of the energy density. You know that. You can do that Poynting vector calculation for electromagnetic radiation and find this equation of state. So this is a relation between pressure and density of radiation. You can even have dark energy where given any positive energy density of what we call dark energy, the pressure exerted by it is negative. Okay, and so this is why gravity is attractive, but dark energy appears to have a property where it is only making matter recede from each other, but at an accelerated rate. So it's it has a realization of the kind of as if it's generating a force which is repulsive, opposite of the attractive force of gravity. So these are equations of state, and these therefore define different T alpha betas. Okay. A special T alpha beta will be one where all of these are zero. Okay, that is vacuum. So rho is zero, P is zero. Now, Einstein's equation is what is going to bring us almost to the end of my lecture. So I already mentioned of the principle of equivalence. That was the key in Einstein realizing that gravity is but space-time curvature. It is all pervasive, and it is caused by the presence of stress energy momentum distribution, for example, of matter or radiation or even dark energy, right? But what curvature quantity can be made proportional to T alpha beta, with alpha beta up or down? Remember, to bring them down, you just apply the metric tensor twice. And that is what I motivated on the previous slides with the Bianchi identity, saying that if you wanted to equate the Ricci tensor R mu nu to T mu nu, then you will be restricting the possible types of curved spacetime you have, but allowing the Einstein tensor T mu nu to be proportional to the stress energy momentum tensor T mu nu is not restrictive because this obeys the Bianchi identity, which is the covariant derivative of this vanishing. And we know that we even want it because we want energy momentum conservation, which is the same thing as saying that the covariant derivative of G mu nu should be zero. But the Einstein tensor G mu nu in terms of the Ricci scalar and Ricci tensor is exactly this. So this is nothing but the same Einstein equation. So this is one of the main deliverables of this lecture package. So you know how Einstein equation came about, but its proof is really in its applications, right? The fact that it actually explains the curvature, the space-time curvature around the sun, which in turn explains the bending of light and Mercury's perihelion precession, all of those things actually can be obtained by solving this. And with a very good approximation, you solve this exactly, but for the approximation that the space-time around the sun is mostly static and spherically symmetric. Okay, so here again, because of lack of time, I'm going to be a little quick, but believe me when I say that general spherically symmetric metric can be written like this, where I'm motivating this metric from the fact that in 3 dimensions, r, theta, phi, okay, it says d omega is nothing but d theta square plus sine square theta d phi square in those polar coordinates, right? So I'm saying that the 3-dimensional spherical metric is exactly like this, okay? but I should allow for the GRR coefficient to be not 1 because these need not be flat. And similarly, I should allow for non-staticity, so things can change with time, let's say. And I do need a dt square, because even for a spherically symmetric metric such as Minkowski spacetime, it is spherically symmetric. But in spherical coordinates, I will need a minus dt square, so I need to have that. But I cannot assume that the time component of the metric or the time radius component are non-zero. They may actually be functions of radius, right? They can be functions of time. But if I further impose staticity, that the space-time is not changing with time, then you can show that this is the expression it simplifies to. Okay, these last two terms remain. This middle one goes away because staticity means that if things are changing one way as you go forward in time, if you now look at the same video rolled backwards, you should actually not see things contract, for example, right? So this should go away, otherwise, because you basically get G0R has to be equal to negative of G0R by switching dt to negative dt. That is what I mean by rolling back in time. So staticity requires that nothing changes in time as you go forward or backward. So that is why this term goes away. And then that leaves me with just this first term. But further, it requires that none of these coefficients are changing with time. All of these coefficients, they can change in space, but not in time. And because there is spherical symmetry, G00, GRR should only depend on the radial coordinates. So because of the signature I used, I can explicitly take this as negative of some positive quantity, and this exponential makes it explicitly positive. And similarly, GR can be made explicitly positive as e to the 2 lambda. And here phi and lambda are both functions of R. Okay, if you use this metric, then you can take the derivative of this metric, and thankfully they're just radial derivatives, except for the sine theta square hiding inside it. Okay, and from those derivatives you can find the Christoffel symbols. From the derivatives of the Christoffel symbols, you get, what do you get? You get the Riemann tensor, and then ultimately you get the Einstein tensor, G mu, big G mu. So this is something you can prove. The components of the Einstein tensor, GTT, GRT, G theta, theta, G phi phi, all of these turn out to be just radial derivatives. The prime here, actually, these are radial derivatives. This should really be R. Okay, so all of these, right, all of the Einstein tensor components are radial derivatives of phi or lambda. Okay, but if it is vacuum spacetime, as again is a good approximation to the spacetime around the sun, then T mu nu, the stress energy tensor, is 0 everywhere, which means the Einstein equation tells us that all of these Einstein tensor components have to be 0, which means that I have to solve just second order differential equations for phi and lambda. Okay, these equations are set to 0. So these are the type of equations you get. So just get the flavor. Don't worry about the details because you'll see them in the slides later. But you get many of these expressions equal to 0 because Einstein equation tells me that the left-hand side will be 0 when T mu nu is 0. And so you can solve for phi and lambda, and this is the type of solution you get. Remember, they will only have to be radius. M here is an integration constant. Okay, so ultimately for the static metric, GTT gives you 1 minus 2m over R. R is the same radial coordinate here. M is that integration constant. And for GRR, you get 1 divided by 1 minus 2m over R. This is nothing but the Schwarzschild metric. And this defines the spacetime metric around the sun and even around the Earth to very good approximation. Okay, this is where I'm out of time, but I'm happy that we at least now know what the Schwarzschild metric or the Schwarzschild solution, the spherical symmetry in the static metric looks like. And future lectures will use it to describe the spacetime around black holes and neutron stars. And we'll change things a bit to also maybe describe gravitational waves. Okay, let me stop here so that there is at least 5 to 10 minutes of questions I can answer.
Okay, so one question is, so what is, can the cross product be defined in four dimensions?
Can the curved space
cross product?
Sorry?
The cross product, vector product.
Okay. No, when the cross product you know of cannot be defined in that way. But there are generalizations, right? I mean, like I was talking about antisymmetric objects, right? So when you're talking, so there are generalizations of it in that fashion. We did not need it in these lectures, but yes, if you want to study about them, I can actually add a reference in these slides towards the end. Towards the end, I can add a bibliography. Indeed, I didn't talk about, when I talked about dual vectors, I mentioned one form, but yes, the fact is that to simplify the computation of, for example, the Riemann tensor components, you can use n forms. Okay, that would be one quote unquote way of generalizing the cross product, where you have these higher ranked objects, just like r alpha beta mu alpha beta mu. So yeah, alpha beta mu, right? That's like a fourth rank object. You can, but that itself is tensor with mixed properties, right? In some indices it is antisymmetric, in others exchanges it is symmetric. But you can have objects whose symmetry properties you define ultimately by their action on other vectors or other dual vectors. Okay, so basically, remember when I said that the metric is a symmetric tensor, I said the action of G on two vectors, okay, AB, or maybe more appropriately the basis vectors, like E alpha, E beta, right, is symmetric, meaning the interchange of those basis vectors does not change the final answer. Similarly, you can define higher rank forms which are actually anti-symmetric under the interchange of their action, for example, on dual basis vectors. Okay, so you can have multiple dual basis vectors being acted upon by higher ranked objects, so that the result could be anti-symmetric under the pairwise interchange of any of the indices. So you can have objects like that, and they do serve purpose. For example, some of these things simplify the computation of the Riemann tensors. Remember, there are 20 of those that you have to compute of. Okay, another question. I can't hear anybody. Is my connection bad?
I'm sorry. So my question is, another question is, how do we define inertial frames in curved spacetimes?
Good question. I hinted at it, but this question allows me to expand on it. In curved space-time, inertial frames in general they exist only locally in space and time, like that freely falling elevator. Okay, if you have a frame that remains inertial, meaning you can define it to have constant velocity in time and space, then that space-time cannot be curved. Okay, so a curved space-time is one where you have no inertial frame that is global, only locally. But in terms of quantities I defined, we are basically saying that for a general curved space-time, it's always possible to go into a local inertial frame, by which we mean that you can always define at a point in space-time, anywhere on that manifold, a special choice of basis vectors in terms of which the crystal symbol components will all vanish. But their derivatives in general, not all their derivatives will vanish, okay, if the spacetime is indeed curved. So yes, in curved spacetime, you will not have global inertial frames, but locally you will always be able to find inertial frames. And that is something that is consistent with observation, and that is what was given a name, right? The principle of equivalence.
Another question is, how many scalars do we require to get enough information about curvature of spacetime?
Okay, so that is falling somewhat out of the scope of this. There are different ways of defining curvature, right? Like the Gauss curvature and so on and so forth. And once again, I will just refer you to, let me make it. Just look at my bibliography in the slides to read up more about it. I would like to take questions that are more directly relevant to what I taught. For me and for Einstein general relativity, it actually suffices to define curvature in terms of the Riemann curvature tensor. Okay, and as I told you, even in the most general case, the maximum number of elements that it has is 20. Okay, so we do not need any more of those. But if your question is really about different ways of defining curvature, then I will refer you to most likely a book or a paper that I cite in the bibliography. Next question.
So next question is, so if a vector is changing in curved spacetime, so does it mean that the zeroth component will also change, the time component?
Yeah. So in general, we are dealing with four-dimensional vectors, right? And if you are translating or transporting a general four-dimensional vector from one point in space-time to another point in space-time, then not just the spatial components, but the time component can also change. Okay, this is a general translation, and this is not necessarily a parallel transport. And this can make sense, right? So, for example, if you're talking about the sun itself, right? Let us say there are different planets going around different orbits around the sun, but the speeds of these planets are different. The speed of Earth is different from the speed of Jupiter, right? In fact, the Kepler's laws are valid to a very good approximation, and so you know that the velocity of these planets, falls off like 1/the square root of the distance, right, from the sun. So what am I getting at? What I'm getting at is that so these freely falling planets are defining frames in which you can make measurements, right? So imagine that you shine a laser light from a satellite around Jupiter, right? So you can measure its frequency, but the frequency is just related to one of the components of the four momentum vector that defines that light or that photon, right? Because the photon has a four momentum, right? And the four momentum has energy as one of the components. And that energy you can measure standing, say, on Jupiter, right? But as this photon falls inwards towards the sun, and let's say it momentarily crosses Earth, then the fact is that Earth samples a stronger gravitational field from the sun than Jupiter does. And that's a fact. In fact, as we climb the mountain, even Earth's acceleration decreases as we go away, right? So, which means that the frequency of the photon measured by the person on Earth, that same photon, will actually have changed because it is now deeper in sun's gravitational field. Okay, so, and remember that the component we're talking about is the energy component. That's the zeroth component of the four momentum. And how exactly its frequency changes, I actually show that. Yeah, I show that here. Maybe I'll include this slide so that you can see how you can use this short shell metric. So this is a nice application which I ran out of time on. Your question gives me a bit of a time to explain it, but basically the first thing you should find out is, are there conserved quantities, okay, in the space-time? And one can show that yes, because the space-time is static, its components don't change with time. That is why the certain quantities are therefore constant or conserved, and then you use those conservation laws to find, for example, how the energy measured at point 1 will be with respect to this metric component. So this is the same e to the related to the e to the 2 phi I defined for GTT, which is basically this quantity. And then at another point where the radius is different, you have a different quantity, and the ratio of these two actually factors relates the energy at two different points. So this is the frequency where I canceled out of the Planck's constant. The frequency of the photon, let's say at Jupiter, relative to the frequency of the photon at Earth, is given by this expression, okay, which is a function of the radius, the orbital radius of Earth around the sun, and the orbital radius of Jupiter, this planet 2, around the sun. So, and from here you can calculate. I will let you figure it out whether this frequency is going to increase or decrease, right, as the photon falls from Jupiter towards Earth. A hint is that if you were to drop a ball, the ball will actually accelerate. Its kinetic energy will increase. The analogy breaks down because the ball is massive. This photon is massless, but the general trends are similar. So use that as a hint, but you can also plug in values and figure out whether nu2 is less than nu1 or greater than nu1. Any other question?
So one question was, if time is a vector, then in Newtonian physics, why do we consider it a scalar?
Time is not a vector. What is time?
Say to the question.
Remember, energy is not a scalar, right? This is time and again proving that energy is actually the zeroth component of the four momentum vector. Similarly, time is neither a scalar nor a vector. Time is the zeroth component, right? What matters is change in time, right? So the change in time, or the time separation between any two space-time occurrences or events like explosions, right? The change in time, the time separation is the zeroth component of the coordinate separation 4 vector, delta x. Right? Delta x is a 4 vector. Its zeroth component is the change in time, or the difference in time between the occurrences of two events, right? And then, so I am saying the delta x, when I say delta x, I mean x with the boldface, like p with the boldface here. But then there are other components, spatial components, right? There is delta x1, delta x2, delta x3, which are basically the x, y, z separations of those two space-time units. So, and indeed, Newtonian mechanics and Newtonian gravity are, both inconsistent with special relativity. Special relativity is borne out by multiple, observations. Whether it is, for example, how the frequency of a photon will be measured. Okay, when you view that same photon in the moving frame S prime versus when you measure the frequency of the same photon in the classroom frame S, right? All of these relations are verified, and similarly, how clocks will dilate, right? As for example, as they move, all of these things are verified. For example, in the measurement of half-life of radioactive particles, right? Because these particles decay, they have a half-life. And you can measure that half-life in your lab where this radioactive material is static with respect to your lab. Or when it is moving with respect to your lab, there also you can measure the half-life of the particle or that material. And you can see that actually there is time dilation. Right? So all of these things are proven observationally. So that is why we know special relativity is correct. So yes, Newtonian mechanics and Newtonian gravity are approximations. So, and the way they treat time specifically is indeed a big approximation, which holds in weak gravity and slow motion, but not in strong gravity and motion that of particles as close to the speed of light. Right? That is when you see the differences in the most stark fashion.
So one last question. So you gave some assignments throughout the talk.
Yes. Yes.
Are they supposed to be submitted, or are they for their own exercise?
No, these are for your own exercise. And as you know, like any good student, if you're true to yourself, you'll do them, you'll understand the subject better. And I will also add that this is actually not the end, because in 3 lectures, the only motivation was to give you a flavor. Even for the most sincerest of students, I will not expect that with 3 lectures you can understand all of general relativity. So use this again just as a flavoring, but look at many other very good videos online and teaching or reading material that I will give in the bibliography at the end of my slides to follow up, okay, and study more and understand these things more deeply.
Yes, so that's it for today.
Okay, thank you all, and stay safe and healthy.